Good afternoon. This has been a fabulous conference so far. There's been talks by people who are my personal heroes, mentors. I've learned from their papers. I've learned from them directly, and you've seen some of my collaborators as well. Now I get an opportunity to show where we are trying to go with some of the questions, many open questions, in context of designing food emulsions, milk to mayo, using plant-based ingredients. So this talk will include some discussion of fundamentals and maybe very few unpublished results towards the end. This is work that was primarily done initially with a bunch of undergrads, and now I have some PhD students roping in. So this has not been said explicitly this week, so I thought I'll put up a slide or two to say that there are at least 23% of the global greenhouse gas emissions are related to agriculture, and there's a large amount of that comes from just our efforts to get livestock going, whether to produce milk, to produce dairy products, egg, or meat products. And in context of sustainable living and avoiding all the worst instances of climate change effects, we'll need to start thinking about alternatives. And when we want to think about alternatives, this is driven partially by what consumers want, partially by what manufacturers want. So it has everything from trying to design products that have the right taste, texture, functionality, and of course sustainability. But when you actually get to making things, then those things have to be produced, mass produced. There we have to deal with the problems of rheology. The rheology problems that we've seen discussed so far are all related to shear rheology. So shear rheology essentially allows us to understand the response to flows when the velocity gradients are perpendicular to the flow direction. So anytime there's a pipe flow, there's always a stationary surface. Next to a stationary surface, the velocity is close to zero. Then you get sort of a parabolic profile for Newtonian fluids. Whereas whenever in processing we end up with converging or diverging channels, which is usually the case when you're trying to extrude things, for example, or push things through porous media, or even while swallowing, in all those cases, we end up getting streamwise velocity gradients. And these streamwise velocity gradients come with extensional properties, and they require separate characterization, which is going to be focus of the lecture on Tuesday. So in addition to thinking about flows, just because we need to process things, it's very important to understand the flows in context of oral processing. And the oral processing, in addition to whatever we can do on a rheometer, whether it's shear or extensional rheometers will be discussed on Tuesday. You have to remember that in oral processing, there are additional effects that need to be accounted for. There's continuous digestion, dissolution by saliva, and that changes the state of the material. So you might start with one volume fraction of particles or droplets in your food formulation, but as saliva dilutes it, the volume fraction continuously evolves as you chew on things. And there are questions related to digestibility, questions related to digestion and health that are well beyond my expertise, but those all have to be addressed in this context. All right, so coming back to mayo. So mayonnaise legally has to have egg or egg yolk containing ingredients. So in US, you can call something mayonnaise only if it has egg yolk containing ingredients and has more than 65 weight% oil. So that's a lot of oil that's packed into a small amount of water. And if you want to avoid having fatty food, mayo is as full of fat as these things can get. So in addition to egg yolk and vegetable oils, it needs to have some acidifying ingredients, vinegar or lime juice, more than 2.5 weight%. And what this ensures is that what this ensures is all the proteins that are present tend to be in their charged state. So here is a typical microstructure of mayo. It's an example of a dense emulsion. Here the oil drops are packed in a very high volume fraction. They can easily be packed at the volume fractions close to jamming, or even go beyond that transition because these drops are deformable. And also shown here is sort of the foam-like network formed by the aqueous films in this case. So the rheology is determined both by the response of these droplets and this foam-like microstructure that's formed by the suspending fluid, and whatever happens at the interface. And a lot of fascinating things that happen at the interface, how do you characterize them, were discussed in this morning's lecture by Jan. And I'll just ask you to study Jan's lecture and papers very carefully. There are a number of very relevant papers on how the interfacial rheology of plant-based proteins is different from animal-based proteins, from Jan as well as from Peter Fisher. And we'll just remember that there are challenges that are related to interfacial rheology in context of designing foams and emulsions, including mayonnaise. So when you want to make plant-based mayonnaise, one of the big challenges is to remove egg. And when you remove egg, what you have to replace is the emulsifier. The emulsifier goes to the liquid oil interface. In addition to that, egg contributes to the rheological response of also the suspending fluid. So to make up for the emulsifier and the rheological response of the suspending fluid, in addition to proteins, because plant-based proteins are typically less water-soluble and might not have the right interfacial as well as bulk properties, we often need to add polysaccharides. And those polysaccharides allow you to make more stable vegan versions of Mayo, and there are consequences of using those polysaccharides, and I'll try to touch upon some of those in my talk. Now, if we go and look at milk, if Mayo is this very dense, concentrated emulsion, which almost looks like semi-solid, milk, as we know from our daily experience, is almost water-like. And it's almost water-like because what you have here is almost 87-88% is water. It contains a small amount of lactose and minerals dissolved in it. So overall viscosity of that system is close to water. And then on top of it, there are fat globules. And these fat globules are less than 4 to 8%, depending upon whether you have skim milk or whole milk. The absolute concentration of fat globules changes. And these fat globules, which are of the order of a few microns in size, are then surrounded by a fascinating self-assembled structure called the fat globule membrane. And the fat globule membrane has lipids in it. It also has a certain amount of proteins buried in it. And how many lipids are there and what proteins are there really depends on the processing conditions that this milk faces. So most often when we get milk at home, at least in the US, it's homogenized. And what you mean by homogenization is you take milk as received and pass it through a process so that you can reduce the drop sizes, and this allows you to have greater shelf life. So in addition to milk globules, there are proteins present in milk, and there's whey, which is typically present in form of proteins of size less than 10 nanometers, and they are casein micelles. So casein micelles refers to this self-assembled structure formed by a combination of 4 different types of casein proteins. These can be 50 to 500 nanometers in size, and in addition to flat globules, these are the particles. Both of these are particles that are present in milk. So overall rheology of milk is determined by combination of contributions from flat globules and these proteins and micelles. So when we want to start designing plant-based alternatives, one key idea is to start making these with plant-based sources that allow you to get the oil phase, emulsifier, and then maybe add some other structurants to affect the viscosity of the suspending fluid. In this case, again, what people typically add is some form of polysaccharide that allows you to change the viscosity of the suspending fluid and give you higher stability for the plant-based milks. How does that affect overall flow behavior is one of the questions that we'll try to come back and address. So as I said, when we try to make emulsions, there's a um, large number of emulsions are made. The man-made emulsions require you to process them using very high deformation rates. And these deformation rates involve very high shear rate flows, very high extension rate flows, which can often unfold proteins, which can even unravel polymers, and polymers can undergo chain scission. And this is something that we should be aware of, especially as we try to design experimental systems for studying the effect of proteins at interfaces. The actual processing, which involves high shear rate mixers or homogenizers, might unfold those proteins, and that would change their bulk rheological behavior, interfacial rheological behavior, and their interaction with each other and with any other suspended phase, including polysaccharides. So this requires an understanding of forced drop breakup and merger, so pinching and coalescence. My friend Marc Antoine already discussed with you how much we like the problems involving drop formation, drop pinch off, drop merger, but everything he discussed was involving droplets that were Newtonian, and it was involving sort of processes where there was no applied velocity field. So some of these problems are way more challenging because of non-Newtonian fluid mechanics, interfacial rheology, and very high deformation rate flows. In addition to thinking about emulsification, then if we want to design plant-based milks or mayos, you have to start to worry about the colloidal stability of these, and that involves questions that have been discussed this week, including what was mentioned in the morning, the role of adsorption kinetics, as well as the role of colloidal interactions. Lastly, depending upon the specific surfactants, polymers, proteins that are added to the emulsion, there can be a wide variety of these at interface. Biosurfactants like saponins, lecithin, these might be found, for example, in soy milk. Polysaccharides, whenever they are added, they can interact with other added polysaccharides and proteins. So then you have to not only think about individual adsorption, but also how they complex with other compounds. And then there can be colloidal particles, including proteins acting as colloidal particles. Egg yolk has some particles, and often starch is added to things like mayonnaise or vegan mayo. So in the talk today, I'm not going to really spend time on thinking about these, but it's important to remember that in a real system, in a real food system, there are way more things involved than we typically study in these clean problems, model problems that we carry out for understanding effect of adsorption kinetics, or studying adsorption kinetics for single protein type or surfactant type, or interfacial rheology measurements that we do with a single system. So overall, what fascinates me in this context is when we want to design any new food formulations, there's a variety of shear and extensional flow problems. The extensional flow problems are involved not only when you're trying to process things, but also anytime you dip into a fluid and you stretch a liquid bridge, or if we dispense a fluid or try to check through the spoon test that every grandmother likes to do, and all of us who cook like to do, to see how thick a gravy is. So these involve these capillary-driven flows, and in the thinning neck, the flow field is such that you get streamwise velocity gradients. So on Tuesday, we'll talk in detail about these flows and how to analyze them and what we can learn from them about extensional rheology response. All right. So Gareth introduced us to the 5 key characteristic rheological responses that we need to worry about. And of course, as we try to emulate milk or mayo like emulsion design, we have to think in context of rheology. We have to think in context of these measurements. What is their rate-dependent viscosity. So here is an example of um, another shake gel. This is a shake gel made by combining silica particles with polyethylene oxide, and most of you got to experience this conversion to more or less solid-like response by shearing it, and on a couple of days back. Then there's stress relaxation modulus, which is a way of understanding the role played by elastic effects that always seem to depend on microstructure as well as the deformation and flow of the ingredients. Then Gareth gave you a good demonstration of normal stress. Yesterday, this can be very important to understand, especially because if you're trying to mix things and you have a fluid that displays first normal stress difference of this sort, you can really short your mixer if you're not careful. And in design of large mixers and industrial processes, the normal stress effects can lead to all kinds of instabilities. Last but not the least is the role of extensional rheology. So shake gels, as well as this example, are here to illustrate that when you put polymers together with particles or other ingredients where they can interact with those ingredients, the resulting formulation, multi-component formulation, can have some interesting rheological response. So here is an example of mixture of silica particles and two different polymers. One is a polysaccharide, hydroxyethyl cellulose. The other one is polyethylene oxide. The big difference between these is that polyethylene oxide is very extensible. So we start with similar coil size, which means the shear rheology of PEO solution and HEC solution is exactly matched, but there's a big difference between how much they can extend. This affects mainly their extensional rheology response. And then if we mix the same amount of silica particles into these, the consequence on the rheology of the mixture is very easy to see. In one case, you get pronounced stringiness. In the other case, there's no stringiness. So again, how stringy your ketchup or mayo is a real problem, and we are now funded by Kraft Heinz Foods for thinking about this kind of stringiness problems. Which brings me to the case of Mayo. So I was amused to see that now finally the Gareth and Randy and Chris have agreed that they should include yield stress as the fifth element here. So here I'm trying to dispense Mayo, and as you try to dispense Mayo, something fascinating happens. For a while, what you saw was a solid cylinder being extruded. So it really extrudes almost like a solid for a while. And then when this weight becomes large enough, larger than the yield stress, so weight divided by local area becomes larger than yield stress, then finally there's a transition from a solid-like response to a liquid-like response, and this falls off. So controlling yield stress can be important if you're trying to dispense things, or you're trying to 3D print things that are made with very dense emulsions or suspensions. Since this is a food conference, it's, I guess, important to again mention that when we think about viscosity, this is the entire range of viscosities that you can encounter in many common food products. Picking example of milk and mayo allows you to sort of look at a case where you're near water-like with milk, and at this very high viscosity case with mayo. The most food materials have both viscous and elastic properties, and if you want to get a sense of what a typical modulus value feels like, here's a calibration curve based on tofu to popcorn kernel, and you can go from, say, 6 kilopascal to 325 megapascal. So far in this conference, we've seen some examples of how choice of polymer concentration affects their overall rheological response. There's been some mention of entangled polymers as well as worm-like micelles. In fact, if you want to understand structure and rheology of complex fluids, these are the 6 separate cases that one can think of. And by understanding how individual elements like droplets in case of emulsion respond to an applied flow field, we can start to build models that connect to the properties of individual dispersed particle, droplet, polymer, surfactant, or self-assembled structure. So this is something that we'll try to go back to. So I am a polymer physicist or polymer rheologist by training. So when I wanted to start thinking about emulsions, my starting point was to first remind myself how we think about response of polymers to an applied shear flow. So in the case of polymers, what we have is in a shear flow where velocity gradients are perpendicular to the flow direction, a polymer coil gets mildly perturbed. And when it gets mildly perturbed, it starts to stretch and align with the flow. And this leads to a decrease in viscosity with increase in shear rate. So you often observe shear thinning with polymer solutions. If we stop the flow and observe the polymer coil, it goes back to its unperturbed state, because that's the entropically favored state, over a time scale called shear relaxation time. And Gareth mentioned this, that this shear relaxation time, in some sense, is the ratio of viscosity to modulus, so it captures the effect of elasticity. In extensional flows, you need to remember that the velocity field is different. You have streamwise velocity gradients that give rise to an extension rate. In response to that streamwise velocity gradients, the resistance to flow is really captured by extensional viscosity. And here, polymer coils can get perturbed to a very large extent. This is a rotation. This is a flow field that is shear free or lacks rotation. So polymer coils can get really stressed. And then if we stop the flow, this is hydrodynamically a very different object. So it might take a very distinct relaxation time to get back to the entropically favored state. So what happens now if we go and think about emulsions? So if we think about emulsions, the simplest case would be to start with a clean interface. And if you start with a clean interface, the emulsion droplet has its own viscosity. In this case, we are specifying that viscosity by using mu times lambda. And unfortunately, we rheologists love to do this. We use same symbols for meaning very different things. And I apologize for this. We hopefully, in 20 years from now, we'll all become consistent. But in context of my talk, what I should emphasize is for the dispersed phase, the viscosity is mu times lambda. For the outside fluid, viscosity is mu. Whenever we refer to the viscosity of the entire emulsion, I'll use eta. So defining it this way allows us to remember that the viscosity ratio is lambda. Then there's a different density of the dispersed phase and suspending fluid. They need not be matched. I've used sigma for surface tension this morning. It was gamma. And my friend Mark was using capital gamma. So hopefully you'll remember that sigma for me means surface tension. So in a shear flow, a drop, again, just like a coil, gets mildly perturbed. And when it gets perturbed, it has, say, an ellipsoid-like shape. Taylor was the first one to start analyzing what happens to a drop in presence of a shear flow and extension flow. And he defined two parameters. We call one of them Taylor deformation parameter. This Taylor deformation parameter depends on the length and breadth of this ellipsoid. And in flow, there's a certain alignment or orientation angle represented by theta. Now, in case of an emulsion droplet, the elasticity arises from the fact that surface tension wants the droplets to be spherical, and this leads to an elastic effect that is of the order of surface tension divided by A, which is size of a droplet. So surface tension divided by A gives you the same dimensions as of a modulus. So viscosity divided by surface tension multiplied with A gives you a time scale. And I guess I should have replaced this with tau, which is what I use everywhere else. So when you multiply the time scale with the deformation rate, which could be, the G could be an extension rate or a shear rate, then we get a dimensionless group called Capillary number. All right. So in case of polymer solutions, Pete Olmsted mentioned that we start by discussing dilute solutions where polymer coils don't affect each other, and you can consider the response of a single coil and learn a lot about polymer solution behavior for dilute solutions that way. And then once you go below an overlap concentration, there's partial overlap. Um, the degree of overlap increases as you increase the amount of added polymers in this semi-dilute solution. And eventually, you get into an entangled state where topological interactions play a role. And this leads to the increase in viscosity in a dilute solution. You have almost linear dependence on concentration. It gets to be much stronger in the semi-dilute solution. And once entanglements are involved, get to even stronger dependence on concentration. So this is the kind of formalism we also saw in context of colloidal dispersions. Again, in colloidal dispersions, the viscosity increases as you go from dilute to concentrated systems, and where exactly it starts to rise very strongly depends on the closed packing volume fraction, which is very easy to define for hard spheres, but not so easy to capture for some of these deformable particles. So you can think of emulsions as deformable particles, and if you think of them as a deformable particles, then we would expect something similar to happen for emulsions. And not only we have something similar happen for emulsions, but just like for particle suspensions, if we remember from George's presentations, for particle suspensions, as you increase the volume fraction, you go from this liquid-like response to a response that's described by Herschel-Buckley model in this case, or it's a characteristic response of a yield stress fluid. So there's a minimum stress that you have to apply to get flow going, and at high deformation rates, we get this power law behavior with exponent n. So it's kind of fascinating to see that here you have PMMA hard spheres of size 200 nanometers. Similar behavior can be emulated by emulsions, which have deformable droplets. There's some interface, role of interfacial properties, but again, you have a volume fraction beyond which there's yield stress. And so when we think about response of emulsions, here I'm plotting overall viscosity of emulsion scaled by viscosity of the suspending fluid. Initially, you're in dilute case where properties of droplets are not impacted by each other. They are hydrodynamically not interacting with each other, and they are far enough that pairwise interactions are not relevant. Once you start including pairwise interactions, you get to semi-dilute state. And then when you go through concentrated and highly concentrated state, then the interactions are very important, as well as there is some certain amount of caging that starts to take place near jamming. Depending upon the interfacial properties, what's absorbed at the interface, this peak value might change. The peak value might change, and then eventually, for so-called dense emulsions or jam dense emulsions, the behavior tends to be very different. You get a yield stress. In this case, I'm plotting here yield stress or modulus as scaled by surface tension divided by mean size of the droplets. So to understand emulsion rheology of milks, you have to really go to the limit of low concentrations. To think about Mayo, we really end up in this real extreme limit of dense emulsions. So going back to milk, if we want to emulate milk rheology by creating plant-based alternatives, you have to replace the ingredients. So background phase can be water-like. Then there has to be a fat droplet replacement, and the proteins have to come from plant-based sources. So if we look at the example of soy, for example, then there again you can get oleosomes that have, at least structurally, they seem to be similar to milk fat globule in the sense that there's an oil body surrounded by a membrane. But where there's even a bigger difference is in the kind of proteins. The plant storage proteins are not that water soluble, as was discussed earlier this week, and these plant-based proteins that are present also don't self-assemble in a way casein does, so you have to compensate for the role of casein in affecting interfacial properties as well as the bulk properties. And this is usually done by adding polysaccharides, among other things. So the question that you come up with is how do we contrast the rheological properties of animal and plant-based milks? What exactly can be measured there? So to answer this question, we thought, why not start with some of the commercially available milks? These are 2 animal milks, cow and goat, and the rest are plant-based substitutes. When you look through the list of ingredients, what we find is that at least all the plant-based milks, except for the one rice, have some amount of polysaccharide added to it. So all of them seem to have added polysaccharides. And then some of them have, in addition to oil, lecithin present, which can also act as an emulsifier and modify interfacial properties. So they have similar amount of protein content, and they tend to have very small 0.03 to 0.05 weight percent added polysaccharide. And if we try to look at literature as to what are the viscosities expected, there are only few data sets that you'll find. So when we dig through the literature, there are a number of reviews published by Julian McClements, and most of those reviews sort of list these values. But if we try to look for rate-dependent measurement, which I'll describe in a second, then those are all over the place. But what you want to note here is the droplet concentrations for skim and whole milk are in this very low range. So they are more or less in the dilute regime. But when we start to produce heavy creams, then you get to volume fractions of almost 30%. All right. So yesterday, Gareth mentioned this review article by Randy, which describes all sorts of errors that one can make while making measurements on a rheometer. And if you want to see examples of those kinds of measurements, then some of these data sets have those errors. So when we try to make measurements of milk, which is water-like in terms of viscosity, first thing you have to be careful about is choice of geometry. Typically, the Couette geometry allows you to have higher sensitivity, and that's what would be recommended. And if you show these plots to rheologists like Gareth or me or anyone who does rheology for a living, they'll be offended by the use of linear scale, for one. So this doesn't really tell me how low in shear rates they really went to. The papers mention there's large amount of shear thinning observed, but it seems that most of that shear thinning might be due to errors that are related to not being aware of the low torque limit and some of the interfacial rheology effects, which I guess are manifested to some extent in almond milk data here, and maybe also in this oat milk data. So when we do these measurements carefully, use a double gap, then you find that at low shear rates, you start to run out of the capabilities of the rheometer very quickly, plus you have some interfacial rheology effects. So cow and goat milk, more or less 2.5 times water viscosity, whereas all the plant-based milks except for rice seem to have this very pronounced seem to have a shear thinning behavior. The viscosity is more than an order of magnitude larger than typical animal milk. So if we go and look at the ingredient list, we find that 5 of these plant milks have polysaccharides added to them. The most common polysaccharide we found was gel and gum. So we requested the supplier of gel and gum, CP Kelco, to send us their most popular milk additive. And this most popular milk additive is the high acyl gel and gum. So at 0.04 weight percent, which is the upper end of the concentration milk producer tend to add this, you find it has a very nice shear thinning behavior. There's also another version of gel and gum, which we also got from them. Both of these tend to have similar shear thinning behavior, and this is quite comparable to the shear thinning observed in case of plant-based milks. So the presence of polysaccharides leads to shear thinning that's typically present in these plant-based milks. All right, so when we go back to this plot and we want to understand how to think about food emulsions, one alternative way to think about designing food emulsions is to go back and try to understand from the fundamental perspective what is known about the role played by volume fraction, response to shear or extensional flow, and interfaces. So to really understand that, you can start with first looking at all the dimensionless variables. In this case, you have an object that's suspended in another fluid. So among other things, you have to worry about the effect of gravity, buoyancy, and compare it to the capillary stress. So when we do that, this is bond number. It turns out most of the theories that are given out there think of suspended fluid and dispersed fluid with the same density. So they believe in density matching. So bond number effects are not typically included. Then the effect of deformation rate is accounted by capillary number. So capillary number can be thought of as a comparison between viscous stress and capillary stress. Or if you prefer, you can think of this as a ratio of two velocities. So shear rate multiplied by the size of the droplet gives you the velocity that's applied, whereas the ratio of surface tension to viscosity gives you the Maragoni velocity, or velocity that depends on intrinsic parameters. Alternatively, you can think of it as a ratio of two time scales, a deformation rate and a shear rate. Then this morning there was a discussion of interfacial rheology effects. Those can be the importance of those can be judged by comparing interfacial viscosity to bulk viscosity multiplied with a length scale. So the shear Boussinesq number and the dilatational Boussinesq number, again, most of the theoretical effort assumes that you can neglect the interfacial rheology effects. And then there can be Maragoni stresses, which could be due to variation of interfacial tension at the interface, as well as adsorption kinetics effects. So there are all these parameters that one needs to worry about. And then the most easy way to proceed is to start with a small deformation theory, where you imagine that the droplets are not getting deformed too much. So even though the image here shows these are almost ellipsoidal, you have to imagine a small perturbation away from the spherical shape. And that small perturbation away from the spherical shape is captured by this distortion tensor, which then is computed by really solving for flows inside the droplet, outside the droplet. It's nice mathematics, involves spherical harmonics and so on. The end result is the velocity at the interface involves these three contributions. There's rotation, there's deformation, and restoration. So deformation depends on the shear rate. Restoration depends on the role played by capillary stress. And here, the way these are written out, what we want to emphasize is the small deformation limit can be reached for two different cases. You can have highly viscous drops when the viscosity of dispersed phase is much higher than the suspending fluid. In that case, the drop rotates faster than it deforms, so it remains nearly spherical. And the other case where you get the small deformation limit is when you have really low viscosity drops. In that case, the drop relaxation time is really fast compared to the deformation time, and so the drops again remain nearly spherical. So for the small deformation limit, it's possible to proceed analytically and really capture the influence of increasing shear rate on increasing deformation. So it's linear in capillary number, and it's linear in uh, in the shear rate, and then there's a restoration term which depends, among other things, on viscosity ratio. So once you take this into account, it turns out that the first theory for dilute suspensions was proposed by Einstein in 1906. Um, then the first effort to describe rheology of emulsions was made by Taylor, who also came up with the deformation parameter. After Taylor, in 1950, in 1950s, Allroyd came up with an expression to describe the viscosity at higher concentrations, and gave an effective medium theory version of this viscosity formula. Then in 70s, the small deformation theory became really popular, especially with the work by Ekrivos and co-workers, and they developed formalism that allows you to calculate both the contribution to shear rheology as well as the normal stress differences. Again, these tend to have dependence on the viscosity ratio. This is typically a weak dependence. And then in the normal stress, you find dependence on capillary number. So if you go to higher concentration, most often the viscosity variation with composition is described by some version of Kraiger-Doherty models. And then Choi and Showalter extended the small deformation theory to semi-dilute solutions, so you can go to almost volume fractions up to 0.2. So this involves some second-order effects, at least involves some second-order effects. And then there are other empirical models, many of them proposed by Paul, that he describes in reviews every 5 years. There's a new review with additional data sets included and compared to the empirical expressions like this one or this one. When you go to jammed state, then you have to describe the yield stress and modulus. There are at least 2 or 3 expressions. The oldest one, or most often used one, is from Brinson and Chris. This should be 1987, not 2017. And here there's again the dependence on surface tension divided by size. So you can take this to the other side, and you find that the yield stress depends, or the modulus depends weakly on composition, at least according to Princeton and Chris. So there have been some attempts to account for at least the effect of surfactants, starting from 1980, Flummerfelt, and then more recently by Petya Vlaskova and Vivek Narasimhan. But there are hardly any attempts to really look at concentrated emulsions analytically. There are some numerical methods available, and there are hardly any attempts to look at the systems that would be most realistically similar to food systems, because food systems have both interfacial rheology effects, so viscoelasticity at interfaces and viscoelasticity in bulk. And this, of course, means there's a lot of open challenges. So any experiments we do can become the fodder for theorists later to compare their data sets against. And if you're a theorist, then this is one of the problems that you could start to think about. But with the analytical expressions that are available so far with the small deformation theory, it's important to emphasize that the small deformation theory does pretty well for dilute and semi-dilute systems. So Taylor's results are really applicable for very low concentrations. And by showing composition on a log-log plot, you can see that the agreement is almost exact for dilute systems. Choi and Showalter capture the first onset of nonlinearity, whereas Kraiger and Doherty, which is an empirical model, can be used to fit most of the composition dependence. In the dense emulsion case, there are at least 2 different models. The Princeton model captures yield stress data sets for maybe more polydisperse emulsions that they were comparing to, whereas Mason's data set is compared to these very highly monodisperse emulsions, and has a different composition dependence. All right. So in the last few minutes, what I'll try to now go back to is at least illustrating the difference between a real and vegan mayo. Again, mayonnaise is very important, especially for our Belgian friends who like to dip their fries into mayo. So when you dip a fry into mayo, that is essentially an extensional deformation, but the rheological properties of mayo determine things like the shelf life. They determine how much mayo will disperse into the basket of fries. They determine the coating thickness, and they influence how easily you can dispense mayonnaise. Finally, these affect also the rheological response in our mouth. Our mouth is a great rheometer, and whatever we learn from the oral rheometry, we call it texture. And texture is always hard to define because it involves not just rheological response, but also a lot of psychological training that we undergo based on where we grow up and our culture. So now if you wanted to make a real mayonnaise, the process, because this is a food conference, there should be some recipes. So at least now you'll see some recipes. So if you want to make real mayonnaise at home, all you need is right amount of egg and oil, and you can go through the process by using a simple hand. You can by whisking simply with your hand. Again, if you want to make plant-based version, it turns out that whisking with hand is not going to do the job. You really need to impart a lot of energy, and so it's typically recommended in all recipes you can find anywhere to have an immersion blender at hand, and most of the recipes involve some thickener like guar gum or xanthan gum that needs to be added. Or sometimes it's just things like brown rice syrup, which have high viscosity. So again, real mayonnaise recipe. If you go online and you look for vegan mayonnaise recipes, you find all kinds of examples. There are examples which involve use of chickpea. So the chickpea is if you soak chickpea overnight, then the fluid that you get is called aquafaba. So aquafaba is typically used as a starting point. So there are no eggs present. In this case, you have to again start with emulsion blender for best results. Right. So another recipe, you can make vegan mayo from vegan milk. So milk to mayo transition can be done by using the right mixing process, which again involves food processor or immersion blender. And most often when you go and read these recipes, they'll show you pictures which more or less illustrate the example of proto-rheology. People are trying to imagine what this should flow like, and by taking pictures, they illustrate that this has the right consistency or viscosity according to most chefs. Then there are some recipes that claim to be oil-free, but this one, for example, had cashew, and cashew nuts also have oil in them, so I don't think it's really oil-free. Anyway, so to make a comparison between real mayonnaise and vegan alternatives, my student Nadia started making her own real and vegan mayonnaise, which we've started to study as well, but here I'm only showing you some data sets from commercially available systems. So commercially you can find at least Hellman has both real and vegan mayo available to you, and Sir K also has a real and vegan mayo available. And if you look at the list of ingredients, you find that all the vegan mayos have some extra ingredients. They have starches or polysaccharides added to them, and these are needed so that you can get the right amount of shelf life or stability. So it's fascinating to see that if you take Hellman real and Hellman vegan mayonnaise, and you just do a viscosity measurement, the viscosity as a function of shear rate turns out to be quite comparable. And this is by design. So they added just enough polysaccharides, played with the ingredients long enough so that they get something that looks rheologically quite similar in this measurement. This is great because that allows them to use more or less the same processing equipment, same parameters to fill bottles, to run their processes. And of course, when you're making measurements of dense emulsions like Mayo, you have to use roughened geometry. You have to avoid the errors that arise with yield stress fluids. So by having this kind of rate-dependent viscosity response, all Mayos that we looked at had similar response. You can ensure that there's relatively high viscosity at low shear rates. This enhances shelf life. And then this viscosity reduction with shear rate is helpful because it allows you to have lower viscosity while swallowing, or this dramatic reduction in velocity helps you to spread Mayo on bread or on sandwiches, and at even higher deformation rates in dispensing. What this does not include is any discussion of extensional effects, and those we'll discuss on Tuesday. So all Mayo emulsions, if you plot stress versus shear rate, you'll realize that they are yield stress fluids, and their rheological response can be described by noting that at low deformation rates, you need a certain amount of minimum stress to get them to flow, and at high shear rates, they have the shear thinning behavior, which can be captured by Herschel-Buckley, that involves yield stress and a power law term. Almost all real Mayos have similar yield stress of around 130 to 160 Pascal, whereas the vegan Mayos are all over the place. Here, most of these vegan Mayos have different amount of added polysaccharides. We don't exactly know how much polysaccharide was added to which, so making comparisons is slightly trickier because you don't know the properties of suspending fluid, the properties of the interface, and those are the kind of challenges we face when we pick a formulation that is lacking in details. But what I want to leave you with is this idea that even though for Hellman Real and Hellman Vegan Mayo, the rate-dependent viscosity looked quite similar, so most often people just try to match the shear rheology response. When we try to dispense it under same conditions, similar nozzle size, similar flow rate, this is what you see. So real Mayo almost extrudes like a solid and goes on for a while. Vegan Mayo breaks off much more quickly, has a slightly different drop shape. So even though their rheological properties, shear rheological properties seem quite similar, they are very different in terms of the time scale needed for dispensing. They are also very different in terms of neck shapes that you get and the drop sizes that get dispensed. So why is that? We'll try to discuss that on Monday. But what I hope I've emphasized for you is when we start to think about emulsions, whether it's dilute emulsions like milk or dense emulsions like Mayo, designing these involves questions that involve thinking about how drops deform in presence of an applied flow field. Role played by surface tension was mentioned in some of those models that I described. Most of those models do not include detailed discussion of interfacial rheology effects. When we go to any realistic food systems, we have proteins at interfaces that give pronounced dilatational as well as dilatational viscosity as well as moduli, and all of those affect things, including what happens to these drops during emulsification process, during storage, and of course during flow. All right, with that, I'll be happy to take questions and discuss more as the opportunity arises. They don't. Yeah, I think we psychologically also know that we are doing this experiment, but they do seem to taste quite different. And there is some nice detailed discussion in papers by Jason Stokes about as soon as you put Mayo into your mouth, then there's a series of processes that take place that involve breakdown of Mayo into smaller bits, and as that happens, there's dilution with saliva, and I think the The change in rheology in presence of saliva tends to be very different based on ingredients, and also what ingredients get coated on your tongue and cheeks is different, so that changes the mouthfeel. But how do you assess that mouthfeel experimentally in the lab is a challenge. Yeah. For this, yeah. So here, I think one of the easy things you can do is this length. So you can measure the length. That length or volume determines. So if you know the density, then you can calculate the weight. So that weight divided by this area gives you an effective yield stress, extensional yield stress. So so you have to exceed the yield stress, and how long this goes on before it breaks off really depends on the extensional yield stress. In a real experiment like this, some of it is getting influenced by deformation history as well. Yeah. Yeah. You can use same oil, especially when you do the experiment, you can use the same oil. So at least the oil phase can be the same, but then what we perceive depends on what gets dissolved in oil phase and um, among from the proteins that we add from plant-based proteins. There's also some discussion about how plant-based proteins might not be the best in providing you the right taste and interfacial properties. So the feeling that you get or mouthfeel you get is quite different. Then. Yeah. Because they try to have similar amount of fat content or oil droplets, and there's no casein present. So the overall stability, they don't hit the right stability till they have significant addition of polysaccharide. And so I think that's a problem that can maybe solved by thinking about an alternative where instead of casein micelles, you have um, one possibility which people are exploring is to use precision fermentation to make proteins like casein. People have succeeded in making whey, but casein is a little more tricky. So then you can have those particles in the background. So maybe by using some kind of nanoparticles in the background, we might be able to get the same kind of rheological response without needing the polysaccharides that are giving significant shear thinning and higher viscosity. And of course, I talked to a food scientist who told me that whenever she tastes the plant-based milks that they're producing, she can feel the shear thinning, their shear thinning. I don't know how you can feel shear thinning in your mouth, but maybe some of you can, or some of us can. Yeah. Um, so when we started out, we just wanted to have a sense of what are the challenges involved. So we try to look at what would be the easiest thing to try. And at that time, the graduate student Nadia was also an undergrad, so I was trying to do this initially with some undergrads, and of course, if you look at the real recipes, then you need to source a plant-based protein. You need to, and there is a lot of variability in the properties of which plant-based protein you pick, and even for the same plant-based protein, it seems that there's no standard protein where you can reliably say these are the properties that we are really looking at. So I thought it would be a good idea to at least have a sense of where the commercially produced systems stand.